All right, we got the countdown. Oh, I gotta jump off camera and mute myself too. All right, good luck, guys.
Good day, everyone. My name is Ed Davis with Enertech Global, and I'm here, Vice President of Sales for our company. And I'm proud to introduce a friend, a colleague.
Wait, Ed, sorry, 1 second. Wait 1 second. I'll get 1 second.
Sorry about that.
No, don't worry. That was we didn't communicate that. All right. Now you can go.
Good day, everyone. My name is Ed Davis with Enertech Global. I'm the VP of Sales for our company, and it gives me great pleasure to introduce Michael Riddler today. As you know, Michael is General Manager and Hydronics Trainer at Eden Energy, but he's much more than that. He's a good friend. He's a colleague in the industry, someone who's trusted, who's been through the paces over the years. And I'm just so appreciative that he's looking at the Advantage Air to Water product today. The industry is looking for something like this, and I believe Michael has a wonderful presentation at hand. He's helped many contractors through his support of the technology, doing many trainings up in the Canada area, all over the U.S. Via internet. And I just know he has his eye on a lot of this type of market industry, and we're just proud to partner with him in this regard. So, Michael, I look forward to hearing more and learning more. So thank you for your time today, and good luck. Thank you, sir.
Yeah, thanks, Ed. Appreciate the introduction. I think it goes without question. I value the support of yourself and Tim and Justin. You guys are great people first and foremost, and working with good people makes it hardly feel like it's working. So today we're going to cover integrating hydronic heat pumps. We're going to talk a little bit about hybrid heating. We're going to talk about hydronic heat pumps across the board. So when I talk about a hydronic heat pump, I'm referring to either an air to water or a water to water. I think it's important that we refer to it as a hydronic heat pump, because the principles we're going to talk about today, a lot of them can be applied to just about any air to water product on the market. In the same token, it can be applied to water technology. One of the things that we just have to be very, very conscious of is we need to make sure that we do understand the distinction between boilers and heat pumps. You cannot pipe a hydronic heat pump like you would a boiler. And we're going to talk about why as we go through this presentation. I should note as we go through this presentation, if you have questions, ask. It's a one-dimensional presentation. I'm talking to a screen, but we want you to get a lot out of it. So if I touch on something too lightly, or if I don't explain something clearly, let me know and I'll elaborate. So as we look at a hydronic heat pump, and if we talk about some of the winning components to success, the very first thing we need to pay attention to is we do not want to pipe them like they're a boiler, and we're going to talk about why. The other thing we have to be very careful about, and I've got a lot of experience, I've seen this over the last 2 decades, I've been involved with hydronic heat pumps, is you can do domestic hot water with a heat pump, but you need to understand that it's not going to be that Corvette experience that you would with a boiler. Where I'm going with that is we're used to hooking a boiler up to an indirect and having so much firepower that we can heat that indirect very quickly. We can't use traditional indirects as a general rule on hydronic heat pumps, and we need to think outside of the box when we apply this to make sure that we can produce enough hot water with the limitations of the equipment. The other thing that's really important to keep in mind is that buffer tanks on hydronic heat pumps are very important. Some of the equipment we're going to talk about today, you don't need a buffer tank, and there's very specific technical reasons why. Other scenarios, you absolutely need to have a buffer tank. And if you don't put a buffer tank on a boiler, typically what we'll see is the boiler will short cycle. Maybe we're replacing igniters sooner than we should be, having to service the boiler more frequently. If you don't put a buffer tank on a hydronic heat pump, it can be as bad as killing the compressor. So we really, really want to pay attention to the buffer tank and understand what it does. The other thing we want to recognize is the difference in flow rates and pipe sizing. So I talked at the very first about distinguishing between them and piping them properly. We need to understand that hydronic heat pumps have different flow requirements. And because they have different flow requirements, it's also important that we make sure that we pipe them accordingly. So the last slide that I had, you could see the Enertech Advantage Air to Water packaged unit. On this particular slide, I have the System M packaged unit. My goal here is not to talk about products that Eden Energy sells. My goal here is to provide technical knowledge and have you guys apply it wherever you need to apply it. So one of the other things that we see happen a lot is people are making comparisons between a hydronic heat pump, again, an air to water or a water to water, to a traditional boiler. I'm not a sales guy, but we're going to make some numbers up for a second. So let's say that the boiler equipment, your cost is 10 grand and the air to water is, I don't know, 17 grand. What we're seeing is people having issues with that going, it's just way too much money than a boiler. That's not untrue. A heat pump will always be more money than a boiler. It will always be more efficient. And the other thing to keep in mind is that it's a hydronic heat pump, so it can do the air conditioning and the heating. So the days of doing a boiler and a VRF or a standalone air conditioner, we can now achieve a lot with a single package unit that's installed outside. The other thing to keep in mind is that we need to pay attention to the lower water temperatures, and we're going to talk about that. Right now, if we find ourselves in that situation, and we've all been there, if we're honest, including me, where you design a system, you thought you could heat it with 120-degree water, turns out you can't, need to increase it to 130, 135. That becomes problematic with hydronic heat pumps. You need to make sure that you can keep the water temperature at your design point. So you don't want to be doing any sort of rules of thumb is where I'm going with this. Make sure that if you're doing your first hydronic heat pump installation, you have some talented people around you. So that can be either the manufacturer, that can be a great distributor, but make sure that you're future-proofing your design. And what I mean by that is design for the principles right now. Don't design for what you've been taught in the past, because although that's all great knowledge to have, it may not transition one-to-one from what you would do with a boiler as to what you would do with a hydronic heat pump. So one of the things that I really like about hydronic heat pumps is that it is kind of an equalizer from an installation standpoint. So these are 3 units that I have personal experience with. So if you have any questions about any of these 3 units, I can definitely answer them. On the far left-hand side, we have the IBC air to water. So the IBC air to water is the only one shown here that is just an outdoor unit without an indoor unit. What IBC is doing a little bit differently is they have an outdoor unit, and they have some really, really cool control logic that they're going to be launching later in the year that they don't actually need an indoor unit. So they're doing it very, very creatively. And at a future webinar, we'll talk more about controls on heat pumps. The one in the middle is the Enertech. And the idea of the Enertech unit, and actually the System M on the right-hand side of the slide, is these units have indoor and outdoor units. So the concept of this would be is if you've never done a hydronic heat pump before, you may want to consider doing a packaged unit with an indoor and an outdoor. So in the case of the Enertech in the middle and the System M on the right-hand side, you will have heating hookups, domestic hot water hookups, literally connect the pipes where they're labeled on the unit, you're done. There is no engineering by contractor. Now, you might ask, what are the challenges of only having an outdoor unit? Some of the potential challenges are, do you know how to manage low temp heating, high temp heating, domestic hot water, and cooling in one unit? So if, like me, you answered yes, and that unit on the far left-hand side every day of the week, if you answered no, then it could be you want to use one of the units in the middle. So where I'm going with this is these are all fantastic units. There's a lot of great air to water products out there. And what we're going to talk about today could apply to any product you see on the screen here. But as always, defer to the manufacturers and seek guidance from them as well. Some people may ask, why would I do a hydronic heat pump? So in my own house, I had a forced air furnace. I removed the forced air furnace and I put in an IBC 5-ton air to water heat pump. I kept all of my ductwork. I put a hydronic coil in. And some people would say, well, why would you do that? So the reason that I did that is I want to use my air to water to produce my domestic hot water. And I also plan to do room by room zoning using convectors. And we're going to show an example of that later. My house is a retrofit. So for me to retrofit and have more comfort, it made more sense to do an air to water, because as I'm illustrating right here, if you look at the heat capacity of water to air, it is 3,500 times more energy. So where I'm going with that is it was easy for me to run a 1/2-inch PEX line from my basement upstairs to my second floor, and then from there, from a manifold, feed into the different bedrooms with little tiny emitters to provide heating and cooling into those spaces, making them comfortable. If I had to rerun the equivalent ductwork for that, what I would be faced with is instead of running that PEX, instead of running a 1/2-inch or 3/4-inch piece PEX, depending on the load requirement, I would have to rip my entire house out to do a 14/8 duct. Well, obviously I didn't do that. So hydronic heat pumps make a lot of sense. We can deliver a lot of BTUs. We can do much more with a hydronic heat pump than we can with an air-to-air. But obviously, every application has its place. My feeling on hydronic heat pumps is that it's going to be a very small sub-segment of the market, but we're going to see that in the future, boilers are not going to be commonplace. We're going to be doing hydronic heat pumps. So it's important that we understand the technology, how to apply it, and some of the gotchas that are going to sort of catch us along the way. So just very briefly going to talk about a hydronic heat pump and how it works. This would be the same whether it's an air to water or a water to water. What we are doing is we are extracting and moving energy when we're in the heating mode. So when you see a COP advertised for a heat pump where it says it has a COP of 3, what that means is for every unit of electricity, we are moving 3 units either from a ground loop in the case of a water-to-water heat pump, or we're drawing that by moving the energy from the air into the space. So heat of extraction is the term that we always use. We are extracting the energy out of the air, or we're extracting the energy out of the water. The other thing to be aware of is that cold climate heat pumps are able to go to much, much lower air temperatures. Gone are the days where it's -2 and you can't run your heat pump. That's not the case. All of the units that we've looked at, you can see the performance tables, even at -12, they're still, if it's a 40,000 BTU unit, sitting at around 36,000 BTU. So it's not like you're losing the entire capacity of the unit. You do want to pay attention to that, though, that there is that drop off. If we look at cooling, the easiest way to explain the cooling operation is your refrigerator. So when you put the food in the refrigerator, if you put your hand behind the fridge and feel all that heat, that's the same principle as what we're doing with a hydronic heat pump. We're extracting the energy, we're rejecting it outside in the cooling mode and taking all that heat and putting it outside. So the way that this is done is pretty simple. Obviously, it has a compression circuit, it has a reversing valve that shifts inside of the unit. But in the bare principle, this is how a air to water or a water to water would work from the inside. So we talked about this before. One of the key things that we want to be paying attention to is COP. Obviously, whether it's a heat pump or a boiler, we want to make sure we pay attention to our flow rates and our temperatures because that dictates our efficiency. We already talked about heat pumps are more expensive. So if we're going to put in a more expensive appliance, we're expecting we're going to get something back from it. So right off the bat, we're going to get a lot better efficiency out of a heat pump than we will a boiler every day of the week. I cannot think of an exception. I encourage you guys to come up with one and put it in the chat, and we'll see if you can come up with one. So the idea is we want to make sure with a heat pump that we always have optimal flow rates. We want to make sure we have very, very good heat exchange through the unit. And we want to recognize what will happen if we don't have enough flow going through that heat pump and what the end results can be. The other thing that we want to talk about is some of the piping aspects of how we pipe these units. So here, what I've done is I've got a boiler that's tied in on closely spaced tees, as you can see. This would be the older school way of doing things. But the thing that we need to be aware of is, you know, if you look at this and go, why are we still doing this? If you look at modern methods of doing this with a short fat header, which I'm going to show you in the next session, we're going to go to our live fire air to water lab and actually talk about a system that's installed. And we're actually going to walk through some of the components of it. So closely spaced tees, we have to be aware we've got a temperature cascade. So in this case, I've got 2 sets of closely spaced tees. I've set it up on, let's say, an air to water, not a boiler. Well, the maximum water temperature that an air to water can put out, I don't care whose name is on it in North America, is 140 degrees. And at 140 degrees, that's the max. We're not saying we necessarily want you to be sitting at 140 all the time any more than we want somebody trying to run a condensing boiler at 190, 195 degrees. So in this scenario where I've got a boiler that say can do 180 degree water, the closely spaced tees doesn't matter. The temperature cascade doesn't matter because if the first one's getting 180 and you put a mixing valve on it, the very last one still has enough BTUs to heat the space. Well, I have firsthand experience where people have done what you see in this drawing on hydronic heat pumps, and they'll put 9 or 10 sets of closely spaced tees, and the complaint will be the first 3 sets of tees, they have heat. The second set of 3 tees are like, we're getting degrading heat. It's not heating as well as it should. So this really isn't an ideal. It's not a matter of right or wrong. But what I would say to you is I would move away from this mentality, look at a short fat header. It will make sure that every single zone is getting the exact same temperature. It will make sure that if we want that heat pump running at 120 for radiant floor systems, we can set it to 120. We're not setting it to 140 so that the first set of tees is getting a better temperature than the last set of tees. Moving on from that, this is a pretty good example of how you would want to do that. So a nice little short fat header. We're going to show you in a second what that looks like in our live fire lab. It's very simple piping. It's one less pump. It's very easy to remember. Basically, the common piping where you can see my mouse is moving here, we want to make sure that common piping is sized for less than 2 feet per second. So your wholesaler, your distributor, our technical team, whoever you deal with, can actually provide you with a complete package design. Or you'll find there's products you can buy off the shelf that'll take care of this. And we're going to show a few when we get into the next segment. So it's very simple piping. And the most important part is if I'm putting on this a heat pump, then I'm not only maximizing the comfort, but I'm making sure that I've got the highest COP being the coefficient of performance to make sure it's working at its most efficient at whatever water temperature is being delivered to it. The other thing that we talked about earlier is buffer tanks. So quite a few heat pumps do prefer to be put on a buffer tank. The idea of a buffer tank on a boiler is we're used to it for microzones. It's not any different from the standpoint of a heat pump. The difference is if you have a compressor that starts up and runs for 1 minute and shuts off, you're going to have all kinds of compounding issues on that compressor and the refrigeration circuit that can give you grief down the road. So a buffer tank for a heat pump serves basically the same purpose. We want to make sure we minimize the on-off times. As that heat pump starts up, it's going to ramp up and then it's going to find its sweet spot, its modulation point. So for example, if my air to water goes to 90 hertz, the compressor, it's going to fire up to 60, 70 hertz. It's going to find about where it's at based off the supply temperature and what we're targeting and what the return temperature is. And it's going to modulate to find its most efficient spot. So from a wear and tear standpoint, we don't want the equipment banging on and off repeatedly. But on top of it, if we can let the unit run for 10 to 15 minutes, not 30 seconds to 1 minute, it has a significant impact on the performance of the unit. It's not my opinion. That's not, IBC or Enertech or Taco's opinion. That's actual research that you can read that's in white papers. Have added to your own homework on that. The other thing that's really nice about this is that if you get into a situation where you have mismatched loads, the buffer tank will allow you to decouple the system so you can have different flows on the unit side than you would on the secondary side going to your loads. And it also makes sure that the system is going to work properly from a comfort standpoint. So the other thing to keep in mind that's really interesting that's coming into play, and I wanted to share this slide, is that we're seeing really cool new technology coming into the market where we're moving away from buffer tanks and we're now starting to see thermal storage batteries, specifically phase change material. So the idea behind this is this phase change battery would be about the same size as the chair you see behind me, but it's the equivalent to 300 liters of water. So it has 4 times the energy density of a storage tank. So when we look at doing load shifting, you can do a totally different buffer tank only on an air-to-water system or a water-to-water, a hydronic heat pump, where we can charge it with electricity off peak. And this battery is not storing electricity. It's serving as an energy resource. We store our BTUs off peak that we can then use on peak. And really, this is a really cool technology that allows us to use not just renewable technologies, but allows us to offset our loads without getting creative. This pipes up exactly the same as a regular buffer tank. Internally, it's just quite unique in how it's set up. So as we talk about some of these points, we sort of drill down a little bit. Normally, this is an all-day course that we do here at Eden Energy. We're trying to do it in an hour, so I'm moving quickly. As we look at some of the earlier points we talked about pipe sizing and knowing the difference between a hydronic heat pump and what is required for a boiler. And I've given some examples here. So if we look at the 2 to 4 feet per second rule on copper piping with 3/4 inch pipe, 65,000 BTUs, give or take, 1.25 inch pipe up to around 160,000 BTUs. So if we looked at it, for example, on a 20-degree delta T, if I had 1 gallon a minute and I needed to deliver 65,000 BTUs, which is, just over 5 tons of capacity, in a boiler application, I could get away with 1 inch pipe. It would be 2.54 feet per second, because if you look at the math on the right-hand side, if I'm doing a 20-degree delta T, assuming water, it's 6.5 gallons a minute. Well, where this goes wrong on the hydronic heat pumps is the assumption that we're working on a 20-degree delta T. So what I've done here is I've reworked the math, in this case with a water-to-water unit, but the principle applies the same with an air-to-water unit. Water-to-water and air-to-water units do not work on a 20-degree delta T. You cannot get most residential air-to-water and water-to-water equipment to run on a 20-degree delta T because they are designed completely differently. From an efficiency standpoint, so if we took the time to read the manufacturer's manual, we would find out that they typically would like to have somewhere in the 2 to 3 gallons per minute per ton. So if you look at the bottom right-hand side, you can see how that ends up working out. We end up, instead of with a 20-degree delta T, we actually end up with a 5 to 8 degree delta T on our hydronic heat pump, which is where the 2 to 3 gallons per minute comes from, right? So if you look at the drawing, if you look at my slide on the right-hand side where I refer to the boiler at 1 gallon a minute, we know the boiler can do a 20-degree delta T, so we know 65,000 BTUs is 6.5 gallons a minute. Redo the math with an appliance that has a maximum of 8-degree delta T. Okay, so in this scenario, typically it's around the 4 to 5 range. I picked 8 just to be as generous as possible, and we can see that 65,000 BTUs is actually 16 gallons a minute. Well, 16 gallons a minute going through 1 inch pipe, not a great idea. What ends up happening is we have a unit that's not performing very well. We don't have enough flow going through that unit. Now, there's a bit of a distinction here. It's the whole conversation of running versus working right. We want to make sure that we have really good flow because we want to make sure that we've got good performance out of that unit. So as we look at that unit, we also want to make sure that we not only have good flow out of the unit, but we want to make sure that we've got the proper leaving load temperature. If I don't have enough flow through that heat pump, then what do you think my discharge water temperature is going to do? If you don't have enough flow through a boiler, then the temperature gets very hot, the boiler is going to derate itself. So you're going to run into issues where you may not be able to heat the space properly, the boiler could be just short cycling, lots of different weird things can happen. In the case of a heat pump where you don't have enough flow through it, if you're in the heating mode, you're going to end up with high pressure lockouts. If you're in the cooling mode, you're going to end up with low pressure lockouts. But let's say you're in a scenario where that doesn't happen. The unit is still running, but not working properly. If we look at these tables, in this case, I'm picking on the Enertech 5-ton air-to-water unit, depending on what the leaving load temperature is also going to dictate not just the capacity, but the overall COP of the unit. So where I'm going with that is if I've designed this unit, if we look at this graph over here that I'm just circling around with my mouse, if I've designed this unit with, for example, a reverso convector, which is designed to work at very low water temperatures, or maybe a Yaga product, and I design it around a 95-degree water temperature, well, if I don't have enough flow going through that unit, then my 95-degree water temperature is in fact potentially going to be 130 degrees because the unit is what I would call constipated. The water's stuck in the unit, so it just keeps heating the water in the unit until we move it or until the unit locks out. So you potentially could take a unit that should have a COP of 3, which is 300% efficient, and give it a COP of 2 or 2.5 just by not putting the right size piece of copper on it. So the question of $20 of material or a 30-second phone call to your supplier of, hey, what's the flow rate? What should I be piping this in? You can make a negative impact on this system for the entire life of that system. I've pulled up an actual example for you. So if I looked at a scenario where I take, in this case, a 3.5-ton heat pump, and I'm going to feed it with the minimum flow. So you can see over here at 5 gallons a minute, that is the minimum flow for this unit. The recommended ideal flow is 10 gallons a minute. So could I make it work at 5 gallons a minute? I could try. I'd have to have a little bit of a battle of, is it going to lock out? Is it going to work properly? Or is it just going to run? But at that COP of 2.6, if we go back to my comment earlier, if we design around the proper flow rate, which is 10 gallons a minute, we go from a COP of 2.6 or 260% efficient to 3.6. And that's a huge difference. So we want to make sure that when we're looking at these units, we're paying attention to what we're doing with the unit. The other thing that's worth noting is you can actually see the capacity. I'm just moving my mouse around it by the 5 gallons a minute. You also have that capacity issue we talked about. So this particular unit, when I've got 5 gallons a minute going through it, is extracting 21,000 BTUs. Whereas just by increasing the flow rate to the unit, I'm now extracting 26,000 BTUs out of that unit. So as we look at it, we talked earlier about what does it mean if we actually were to underpipe it? What happens if the actual water is not leaving the unit as quick as it should be? I've got 2 nice little graphs on the right-hand side that are showing what the envelope looks like for the operating range for heating and cooling. And so if you look at the dotted lines, the black dotted lines, this is kind of the area we want to keep you in on an air-to-water. We call that the safety buffer zone. So at 120 degrees, an air-to-water heat pump is going to work really, really good. And even if you were to push that up to 130, which is the solid red line, the heat pump's still going to do okay. This dotted red line is danger land. This is, don't go here. This is you holding a bag of sugar standing next to your car going, should I pour this in the gas engine? It's a joke, but that's literally what this red dotted line means. Stay away from this line. So how do we stay away from this line? We make sure that we understand 2 to 3 gallons per minute on a hydronic heat pump. As soon as you redo the math at 2 to 3 gallons per minute, you're going to find that you're actually going to end up with the right flow rates because the 2 to 3 is assuming a 5 to 8 degree delta T, not a 20 degree delta T. By having the right flow rate through that piece of equipment, it means we're not going to have issues with anything happening inside of the unit. So what I mean by that is we're not going to have any overheating of the compressor, which obviously causes problems with the oil. Any of you who are in Trevor Matthews' presentation, he had a great presentation where he talks a lot about different things you want to pay attention to on compressor bearing units. We definitely don't want to overheat it. And the reality is if you have water that's constipated, that's what I call it when it's stuck in the heat pump, this dotted line, you are 100% going to hit it. And at that point, you're going to overheat the compressor. You're going to start cooking lubricants. You're going to break them down. And the reality is it's really bad wear and tear on the equipment. So we want to make sure that we always make sure we have the right flow, the right size pipe, and that we're not trying to achieve water temperatures that we shouldn't. The reality is that most cases when we're going in and putting a hydronic heat pump in, it's going to be a radiant floor system. Maybe there's an air handler on it, but a hydronic heat pump is perfectly paired for a hydronic heat pump or for a radiant floor system, because typically we're somewhere around 105, 110 degrees. And if you look at this performance table, you can see that 105, 110, 120 is kind of the ideal scenario for an air to water heat pump. So sort of continuing, what's going to happen if we do this? Well, we're going to have increased energy usage. The unit is going to cycle a lot more, which is going to reduce the lifespan. So what's going to happen is your heat pump's going to fire up with half the flow it's supposed to have. It's going to hit its thermal limit. It's going to shut off. It's going to clear that thermal limit. It's going to just keep doing that. It's going to cycle over and over and over again until you either fix it or something potentially could fail. So that's where the reduced lifespan experience comes from. The other thing about these units is it's like anything. If it doesn't sound right, it's probably not right. If I walk into a mechanical room and I can hear your heat pump running, not a good sign. If you have an air to water, it's probably outside, same conversation. If I'm standing next to my IBC air to water or the System M air to water or the Enertech, because we have all three installed, you can't hear them running. Like you can hear them, but you don't hear the compressor, you hear the fan. They're designed to be very, very quiet. So it'll be much louder. The other thing to point out is that if you do these things, you're not going to have warranty, you're going to have liability. It's going to cause issues for you that you don't want to have. Really, we can summarize all of these points by, you're already here in training, great start, read the manuals, and make sure you partner with somebody that actually understands this technology and ask the hard questions. Just because somebody says something doesn't mean they haven't misspoken. I can misspeak. I'm sure you guys have all done that too. Make sure you're asking the hard questions and seek out more information. There's a lot of experts that can help you on a variety of different topics. So again, just a little bit closer look at this drawing here so you can see the schematic for it. So you've got the safety buffer, which is this dotted line that you can see is at 140. So there is no scenario where you put a whole bunch of closely spaced T's, the last set of T's you can't heat, so you just turn the air to water up to 150. You'll do that, but it won't last for long. 6 months later, you're going to be back there doing some serious work on that unit. And again, you can see our safety line here, which is about the 125 range, but definitely with these units, you can run them up to 130 and still be quite safe. So as we look at it and say, how hard is it for us to design for a lower water temperature? I get this question asked a lot. This was a real world customer scenario. So in this case, all we did to get the supply water temperature in this new install was we added 100 feet of pipe. So PEX pipe, 35 cents a foot, somewhere in that neighborhood, even if you said 50 cents a foot, who cares? So for you to add $100 of material to this job, what that means is you took a unit that might have had a COP of 2.5, i.e. 250% efficient. You were able to bring that water temperature down to 109 degrees. So now it's over 300% efficient. Where I'm going with this is don't get stuck so much on material costs. I do the same thing, but if you have an actual value proposition to why you're more money, especially if we're only talking $1,000 by the time you put your labor and your markup and your profit on it, you can sell this concept. We didn't do anything fancy here. We literally just put 100 more feet of pipe on it. The other thing that you can do is you can start looking at dry panel systems. So the photo on the left-hand side is my house. So I use the ROW panel product, but there's tons of brands out there that you can look into. The ROW panel product produces 28 BTUs per square foot with 110 degree water. So somebody out there listening to me right now is going, holy Moses, you don't need 28 BTUs per square foot in your house. You're exactly right. So my house where I installed this ROW panel, I was heating it with 90 degree water. So if we go back to that COP table and look, okay, what does it look like if we do 90 degree water? Well, that's where you start to see equipment that's performing with a COP of 4 and above. So think about that. If you're getting a hydro bill with this piece of equipment every single month, would you like it to be 200% efficient, 300% efficient, 400% efficient? That's where these discussions happen. The product in the middle is also a very good product. It's called ROW board. It's 18 BTUs per square foot at 110. It's a ½ inch thick. It's a little bit easier to install. But the reason I have these two is because in my home that I just moved to, I'm retrofitting my house. And as you can imagine, I'm not ripping all the floors out. That's super expensive. That's not a reasonable retrofit. So this last photo here is just showing you a radiant wall we have in our live fire lab. So my plan with the ROW board product is it's ½ inch thick. I'm going to go halfway up on my wall and I'm going to put cheap drywall on top of it. I'm going to trim it out. And instead of having a radiator in the room in the traditional sense, my wall is going to heat the space. Super inexpensive to do. Drywall is cheap. Paint is cheap. I can do it. It's definitely a bonus. So don't immediately start looking at the floor going, I got to rip your tile out. I got to rip your hardwood out. Think outside of the floor, I guess, is my play on think outside of the box. There's lots of different options available from companies like Uponor, Rayhow. There's tons of them out there. Other thing to keep in mind, again, when we talk about cooling with air to water, there's a lot of different options on the model on the market. Some of them are exposed. So in this case, I picked an example. This is called the Reverso product. This product is handled by Leyland Hydronics. Shout out to Matt if you're out there watching right now. He didn't ask me to put this slide in, but it's a cool product. So they have a low wall panel radiator that's heating and cooling, Wi-Fi enabled. You can see they have a high wall unit here. This is a really cost-effective way to put heating and cooling into a house. Spoiler alert, I put this unit into my guest room. So I'm actually testing out this low wall unit. I like it. It's clean, it's concise, it's inexpensive. It's much cheaper than me going, I just put a boiler in, now I've got to do some VRF or whatever the case may be. So definitely paying attention to what the options are that are out there. If you don't want to see it, which certainly comes into play, there's other products on the market. So Myson makes a product called the iVector, I believe. It's designed to go underneath, underneath or recessed into the walls. This particular unit is what's called a Breeza 12. It's designed to be recessed into a wall. So I'm going to be using some of these upstairs. When I told you guys I'd run PEX up to do the bedrooms, I'm recessing these into the walls. I just have to get 1/2-inch PEX to them. They're my heating, my cooling, way easier than running new ductwork. I'm not ripping the walls all apart. It's very easy to get 1/2-inch PEX up into a room and deliver the BTUs I need for these. The other thing that's available to you, and again, just trying to give you guys options to think about, is again, this is a heating and cooling trench style rad. These are designed to go down in rooms where there's tons of glass. The reality is that this technology is typically being adopted by forward-thinking consumers who typically have a higher disposable budget. Those that go in and don't think about this cool technology are probably going to find their competitors doing the work. What I like about this is you can see in the photo is this unit is designed to be just recessed right in front of a glass window or like floor to ceiling glass. I did a project with Robert Bean where we did that. So it's a really, really cool product. And as you can see, it's a heat exchanger with a fan, with a condensate pan, lots of options that work really good on air to water or water to water. As we move on, I want to talk a little bit about dual fuel application so everybody understands the importance of a dual fuel application. I'm pretty sure you're going to run into the scenario where you've sized your heat pump, you look at your design temperature, let's say it's 5 degrees Fahrenheit, you got a 5-ton unit that doesn't quite get you to where you need to be. Now you need to figure out what is your backup source. So a couple of things that we keep in mind is that if we have a buffer tank on the system, we don't necessarily want to be charging that buffer tank. My preference is to let the hydronic heat pump charge the buffer tank and then use whatever your backup heat is to actually heat the building itself. There's no reason to heat and store that energy, but there's a lot of different perspectives. There's a lot of different ways to do it. Happy to dive into that more. The biggest thing we want to make sure that we don't do is that if we have a air to water or a water to water, which we already said, if we put it into 140, the red light goes off and we've got a problem. We want to make sure we never pipe our backup source, whether it's a gas boiler or an electric boiler, that it can inadvertently feed water back to the unit that's hotter than it should be. Now, you might think that could never happen. I would tell you one of the most common tech site visits I have to do is to address this issue right here. So if you take anything away from this slide, pay attention to where your backup boiler is in relation to the heat pump. There's absolutely nothing wrong with taking this dual fuel approach. So as we again look at these three products, the one on the far left-hand side is the IBC product. What's really cool about the IBC product is they have an integrated control, which I'm not going to talk too much about here, but instead of having an indoor unit, they have a packaged control that will do everything for you. So what I mean by that is it'll control multiple heat pumps, it'll manage your boiler backup, it'll control a lot of different things that come into play. So it's a really cool unit. The System M, which you see right next to it, which is in the middle, it's the same concept. So their indoor unit has all of the controls and the logic built into it. So you don't have to worry about what am I doing for backup heat? How am I piping the heating? How am I piping the cooling? That's not necessarily a pro. It depends on your scenario, right? The IBC can be a better advantage depending on who's watching this video and what your skill level is. And then on the right-hand side, we have the Enertech unit. So the Enertech unit is a packaged unit. So outdoor unit, indoor unit, all of these units are cold climate variable speed, just to be clear. So the unit on the right-hand side, I've actually got an open shot of it so you can see inside of it. So when you look inside of this unit, you can see it's got a variable speed pump built into it. It's got an expansion tank built into it. These are actually flushing ports, so you can flush it right inside of the unit. The System M is similar on the inside of it. Right here, you can see that the 9 kilowatts of backup heat is built right into it. So in this scenario, it's a packaged unit, which in some cases could be better than doing a standalone IBC unit. Now, if I'm in a retrofit application, I would suggest to you this could be a better option than this. It all comes back to the scenario. This is not a good, better, best slide. This is literally 3 solutions. All 3 of them are fantastic. You have to pick what makes sense for you. And it might be a matter of it's what your supplier is providing. And if you have a lot of faith and trust in your supplier, then I would definitely encourage you to listen to them and use the products that they suggest. So if we look at the actual piping for heating or cooling, I'm going to show you a couple of options. So this option right here is what I would call a heating or cooling with a manual changeover. Again, lots of different ways we can pipe it, but I want us to sort of look at some of the gotcha moments that will come into play. So if you look at the way it's set up, this is my water to water, which again, if it's an air to water, would apply the same thing. It's going to charge this buffer tank. And so what ends up happening is if any of these loads down here come on and call, the loads are actually drawing from the buffer tank, and all this unit is doing is charging the buffer tank. So in this case, I'm showing a standalone control, which is true. IBC has their own standalone control. And in the case of the System M and the Enertech, a lot of this is built into it. But I'm going to show you guys in the next segment when I go to our live fire lab. The big takeaway point I want you to see here is this boiler. I could have put the boiler on this side, and then it would be actually feeding the water into the actual buffer tank. What I never want to have happen is I never want to get this boiler, or pardon me, this buffer tank up over 140 degrees, because then what could happen is the boiler could superheat my buffer tank, and now inadvertently my outdoor unit, whether it's a water to water or an air to water, is getting superheated with water it doesn't need. The concept here is that we're actually going to make sure that if we've got 120 degree water in the buffer tank, this boiler is only lifting it 20 degrees. We're using this boiler to monitor the buffer tank, and that's what tells the boiler to come on. So the boiler only comes on when there is a heating call, which is a catch it. Again, you got to know what you're doing. Be prepared. Make sure it only comes on with a heating call, not a cooling call. And it'll come on with a heating call when the tank is not hot enough to produce usable heat. So for example, if this was a heating air handler and the air handler is calling, we'll let the air to water or the water to water charge this to 120 degrees. We'll lift it 20 degrees with the boiler to take care of the air handler. The boiler would never come on for the radiant floor unless, for whatever reason, we're in outdoor condition. Maybe it got so cold outside that our 5-ton unit is now a 3-ton unit. We're okay. You know, those 10 really cold degree days, I'm in Ontario, those 10 really cold degree days, this boiler will take care of that and make sure we continue to heat the load. Be careful here. If this is a heating and cooling application, just be aware that you've got an air handler down here and you've also got 2 radiant floor systems. You cannot fill chilled water into a slab. It is a bad idea. You can do it, but there's a lot that goes into it. So it's really, really important that whatever our control strategy is, and we're going to show you one in our lab, is to make sure you're not dependent on the homeowner. So what I mean by that is a suitable answer is not, it's no big deal, Mike, because in the summertime, these 2 radiant floors will never heat. How do you know that? Right? If you're expecting the homeowner to turn the thermostat to the off position, hopefully somebody listening to me is chuckling right now, realizing the homeowner's not going to do that. So you could have this air handler cooling. This could still be calling for heating, and it could in fact be pumping chilled water through the slab, and they could call you and say, hey, why is my carpet wet? The radiant floor has got chilled water in it. So not trying to scare anybody, just trying to make people think outside the box as to what we would do. Here's another way that you can do it. So in this case, and this is actually one of my more preferred ways, I'm using Belimo 3-way valves to divert before the buffer tank. So the idea being here is that my radiant floor loads is where my modulation is going to happen. I've got actuators on it, so I could have microzones. The cooling's a fixed load. And these heat pumps, these 3 that I showed you, are all modulating. So they can compensate up and down to a point. I really don't need it for the cooling application. So the nice part for this is that I can bypass for the cooling. And on top of it, this could in fact be an alt source or a Thermo 2000 product. So it could be doing my heating and my domestic hot water. As we talked earlier, you can do domestic hot water on a heat pump. It will work. I'm doing it in my own home, but don't get into something without doing that homework ahead of time of what does it look like? How do I do it? So the example I just showed you would be how you would do an IBC heat pump. That's how I did mine. This would be the example of how you would do the Enertech unit. The idea behind this is it has an integrated outdoor unit, integrated indoor unit, so you don't have to worry about a buffer tank. This unit does not require a buffer tank. And on top of it, we are prioritizing the load. So what happens is if the cooling calls, there is absolutely no way that we can pump heated water into this slab. So if we look back at this drawing, if this tank is filled with hot water, then we potentially will, obviously we'll be putting hot water here, but you could potentially draw chilled water as well if these three-way valves weren't here. So in the case of the Enertech product, you actually don't have to worry about that. Indoor unit, outdoor unit, very, very easy to operate. This again is a multi-unit setup, so you need to be very, very careful with a multi-unit setup. Make sure you've got adequate flow through these units. Whether you do reverse return or do a short fat header, I don't care how you pipe it. A multi-unit hydronic heat pump, be very, very cautious of how much flow you need to have through those units. The number one thing that gets us is multi-unit applications where they're not quite set up properly and we start to run into problems. So I always say heat pumps are not boilers. Stop comparing them. People see the price of air water. They, kind of freak out and go, well, I can buy a boiler for less. It's true, you can buy a boiler for less, but it's kind of like comparing a Mercedes-Benz with a Kia. They're not the same animal. Make sure you explain the difference. In this case, it's not just a luxury vehicle versus a more, community vehicle. It's a high-end, high-performance, high-efficiency product versus a traditional boiler. Both are great. Both have their needs. Make sure you understand where they're used. Always remember they both do heating and cooling. That's a big thing I like to note. Do not feed chilled water where you're not supposed to feed chilled water. And take advantage of some of the modern technology that's available to you so that you can do cooling. Don't dismiss the fact that you can really, really easy do hydronic cooling in a house using a convector. Again, here you can see a picture of the climate canal. There are a lot of options on the market. There is availability across Canada through all the various wholesalers that are out there. And then think outside of the box. Start to look at things like PCM batteries. So if you look at a thermal storage, the idea behind it is that we can store this energy effectively for off-peak. If I'm storing in a buffer tank filled with water, the reality is the energy is not going to be there when I need it. Something like this is really, really innovative. We can use it for heating. We can use it for domestic hot water. We can use it for cooling. So the concept of storing energy for off-peak is very big. If we were in Europe having this discussion, what they would be telling you is they take these units. So the small unit right here that I've just put my mouse on is the size of a large microwave. They will actually put that in the closet, and that's their domestic hot water. Installed right here in the front of it is an internal element. So I'm saying use an air to water or water to water to charge it. In Europe, they will do that. But what they'll also do is they will charge with this built-in element off peak. So they will charge this thing off peak, and on peak, they will draw up that energy and they will use it for domestic hot water or heating, whatever the application may be. And the biggest thing is this is a P58 phase change material. So inside of this battery, it's very, very heavy. It's hundreds of pounds, is a phase change material that as soon as it phase changes, it has 4 times the energy density of water. So it's the same conversation we're having between water and air on my first slide. Now we're talking about PCM technology. New to North America, much more commonplace in Europe. There's a lot of exciting things coming. And again, it's that future-proof discussion of what you're looking at. A great example for this technology is I have a customer, I'm not sure if he's on the training today. He was faced with retrofitting his commercial building, $600,000 to take out his electric heat for his domestic and go CO2. He called me for suggestions, and what I had proposed to him is let's do this instead, right? So at the end of the day, we can store 300,000 BTUs in a 4-foot cube, and his cost on that was like 40 grand. So we're talking 600,000 or 40 grand. He's keeping the electric because what he's going to do is he's going to charge the battery off peak. The apartment building will charge off the battery on peak. So where I'm going with that is don't assume that these solutions are more expensive. You just don't know that without looking. So sort of wrapping everything up as we go through it, key things to look out for is that if you're doing something wrong with your heat pump, you're going to know pretty quickly. Whether it's air to water or water to water, if it's noisy, there's a reason for it. It's kind of like your car. I know absolutely nothing about cars, but if my tires start making a weird noise, it's like, oh, that's not normal. I should probably do something about that. You'll end up with head pressure lockouts. You'll have customers complain and say, I don't know why the unit runs for a few minutes. It sounds really, really loud, and then it shuts off. Well, you're going to go out there, and depending on the technology on the equipment, you'll see a whole row of high head pressure lockouts. If you don't fix it, I'm sure Trevor Matthews has already told you guys what's going to happen if you don't fix that. Spoiler alert, you're going to need a new compressor. Not a good idea. The most common thing you'll get the complaint about is it's noisy and I never have enough hot water. So again, that's an example where you put a traditional indirect on a hydronic heat pump, or better yet, there isn't even an indirect. You just got 60 closely spaced T's on a unit that can't produce enough higher temperature water for the last set of closely spaced T's, and we just move a few T's in the design. Obviously, comfort issues. We don't ever want to have comfort issues. In the same token, we're going to have performance issues. If we don't have enough hot water, we don't have enough flow, we probably have undersized piping, it's going to result in performance and comfort issues. The other thing you'll see, and we've got first-hand experience with this, you'll have electronic failure, you'll have capacitor failure, you'll have compressor failure, but worst of all, you've lost your best sales tool. That customer that should have been your referral to get you a lot more business, to get you in front of a lot more people, well, now your competitor's in there fixing the work for you. That's not something we ever want to see. So it's really important we pay attention to this. We try to make things go as smoothly as possible. And Leah, I don't know if you're still there moderating for us, but I feel like we did pretty good. We knocked it out in just over 45 minutes.
I'm always here, Mike. Awesome. Thank you so much for that. That was a great presentation. So we don't actually currently have any questions. However, I'm going to slow my speech and hopefully somebody will ask a question as I delay here. Still nothing.
So anybody who wants to see the longer version of this, if you go on YouTube and just look up heat pumps are not boilers, you'll find a longer version of this. If you go to the E-Energy Equipment YouTube channel or the Plumbing and HVAC YouTube channel, you'll find Leah and I doing all kinds of things. The E-Energy Equipment channel, there's actually a lot of training materials where John Siegenthaler and I go through all kinds of great stuff.
Yes, and he's also written an article for our magazine with the headline "Heat Pumps Are Not Boilers." So there's also a written medium if you prefer it that way.
100%. So the plan after this is we're going to go back to the live fire lab. I think that starts in about 15 minutes. Am I right, Leah?
Sure. Sounds right.
Yeah, perfect. So we're going to go back to the live fire lab and we're going to actually show the technology that we just talked about. So we've got a super talented camera guy, Francesco, that's going to attempt to navigate around the lab while we show off some of the stuff that we've got happening there.
Yeah, so we actually have a little bit more time. I quickly checked over to the agenda. So we have at 2:45, we have our the live demo with Michael Riddler then. So
awesome.
We got a bit of time. So if anybody has any questions, I believe the next thing on our next portion of the day on our agenda list is our speed meetings. So this will be the first one of the day. So hopefully everyone gives it a good try. Oh, thank you. I have a question. So this is from, I'm sorry if I haven't pronounced your name right. Sarkis.
Sarkis,
so when using diverting valves, you have them on supply and return lines. Could you talk about why both are necessary?
Yeah, that's a great question, and good to see you, Sarkis. So Sarkis is a good friend of mine. He is a super sharp guy, so it doesn't surprise me he threw out the doozy question. He has some involvement with IBC. We'll see if he wants to reveal that himself. So I've gone back. Oh, I got to share. I went back to a screen to share and forgot to share. Hold on 1 second. Okay, I'm sharing again. So what Sarkis is referring to is I have a supply and I have a return one. And really the only reason I'm concerned about that, Sarkis, is this boiler. So if I didn't have a boiler here, if I didn't have any means that I could potentially heat this tank to a crazy high temperature, I wouldn't be so concerned about diverting. I'm just trying to make sure that I'm diverting through the system completely so I've got complete flow happening where it's not trying to do anything too crazy. Trying to think for all the things that we can't account for. Same conversation we had where the cooling is downstream, where the cooling is here, and we assume the homeowner will turn the heating thermostats off, so it's no big deal. No chilled water will go there. So whether you're using 2 diverting valves or 1 diverting valve, I'm not saying one is right or wrong. Both are certainly doable. It's kind of the conversation of, piping on the return or pumping on the return or pumping on the supply. Depending on what appliance you have, is it a cast iron boiler? Is it a condensing boiler? Where's your expansion tank? You can make a lot of arguments of which way it should be pumped or shouldn't be pumped.
All righty. Do we have any more questions? So Mike.
Thanks, Sarkis.
Oh, we got another one. Wonderful. Thanks, guys. So we got one from Andrew. So in a retrofit application where we don't want to replace existing terminal units or radiators, how can we isolate the heat pump properly if an existing boiler is needed to get a higher, i.e. 180 Fahrenheit supply temperature for peak hours of the year?
Yeah, so that's good to see you, Andrew. I wasn't sure if you're going to make it, but good to see you there. I don't know why I stopped sharing. Let me share again. Let's, okay, so this right here, I don't know if there's a better drawing. I shouldn't say better. Yeah, that's a pretty good drawing. So this would be the scenario, Andrew. So in this scenario, what would end up happening is your air to water. It doesn't matter whether it's water furnace or somebody else's brand air to water. It's going to heat this tank to 120 degrees. And this 120 degrees can probably take care of everything in this house. In your scenario, what you're saying is you've got, I don't want to use a brand name. You've got fin tube, like 3/4 inch copper fin tube out in the house, and we know it needs 180. So the idea of this boiler placement here is we let the heat pump heat this buffer tank as hot as we can get it. So if, for example, it's a water to water, typically they top out at 120 degrees. If it's an air to water, they all top out around 140 degrees. So the idea is I'm going to charge this buffer tank in the case of the air to water to 140 degrees. And this boiler is only lifting it from 140 to 180. So it actually is quite efficient because we're lifting it 40 degrees instead of lifting it, whatever the distance may be. So hopefully that makes sense. This is a pretty common application for it. You're not really like gutting the entire mechanical room. This is the classic. You take a picture, stand back, take a picture. I was going to say stand back so we can see everything. And then we would take and put it in CAD. Most good designers, Andrew is a designer, would just do a CAD drawing of, hey, this is how we would pipe it. Good question, Andrew. Hopefully I answered it.
Awesome. All right. We got some more time. Hey, now they're coming in. Thank you guys. So we got one here from Mitch. So how do I know a heat pump is right for my home? That's a good question.
Well, so it comes down to, is it a new install or is it a retrofit? You could definitely have some challenges in a retrofit application, but Leah's been to my house. We've been filming. So in my own house, we're going to share a whole bunch of footage of what I did. And as I identified, I have no hydronic in my house whatsoever, but I'm working on it. So I honestly cannot think of a situation where a heat pump doesn't make sense for your home. The only place that a heat pump isn't going to make sense for your home, quite candidly, would be your budget, right? One of the challenges I have with electrification, and all for electrification, I'm the heat pump guy. Those of you who know me know I'm always talking about heat pumps. But the reality is we have to give product to people that makes sense for them. So when I talked earlier about a boiler being $12,000, I'm just making numbers up. Nobody hold me to the quote. And the heat pump is say 17,000. If 17,000 isn't in your budget, then you're going to do a boiler. But if it's in your budget, then you're going to do a heat pump. It's the pay me now or pay me later. If you can save up the money to pay for the heat pump now, you're going to pay less every month to heat and cool your home, especially thanks to the new carbon tax that has come into effect. It's really increased this year as well. So I can't think of a scenario, Mitch, where you wouldn't want to do a heat pump, but it also comes down to your own home. If your home leaks like a sieve, then you're going to have to reconsider it. If you need 120,000 BTUs, well, a heat pump and a boiler. Right. So you can always come up with a scenario where a heat pump makes sense, but it comes down to what's the budget.
Awesome. Thanks, Mike. So Andrew actually has a follow-up question for you as well here. So he asks again, what if the return temperature is higher than the 140 Fahrenheit max the heat pump can supply?
Yeah, that's a really good question. So what's going to happen is your unit is going to immediately shut off. It's going to lock out on high pressure. And if you continue to let it do that, you're going to cook the system, quite literally. So I'm trying to think of a good example to give you. I guess the easiest example would be, we just had Thanksgiving. You put your turkey in the oven, you put it to 500 degrees, and you just leave it there for 2 weeks. What's the outcome? Leah's like, sounds delicious. That's what's going to happen. That's my most basic principle. It's going to smell bad. It's going to sound bad. I don't know. Does turkey sound bad when you cook it to 500 degrees for a week?
I'm sure it's starting to sizzle and then doing something else.
Yeah. So the reality is your heat pump will do that too. It'll make weird noises. We talked about that. If you burn it up, you'll smell it. I was at a heat pump where they were running it at 150 degrees for probably a month before somebody called me and said, something's not right. And I could smell burning plastic when I walked in. Now you might ask, but there's no plastic on the compressor. I'm like, no, but it's the terminal connections to it all burnt off. So it was in the process of killing itself. Unfortunately, I was right. The units did die about a week later, and I'm not happy about it. We're talking about this. So if the return temperature is higher than 140, it's going to be a problem. A lot of equipment is smart enough to figure that out. Like I can tell you for a fact, the IBC unit will shut itself off. The Enertech and the System M, I can't say for sure that they will shut themselves off. But part of what we do here at Eden is every single product that we see, wherever possible, we install them in the lab, we play with them. And the reality is we intentionally try to break them. We will do to this equipment what we know people will do, and we give that feedback back to the manufacturers. And manufacturers do care. They do not want their equipment failing, because even if the equipment fails due to something I did, it still hurts them. It's still their brand. It's still their reputation. And they know I'm still going to want warranty. So they're better to train me and be like, don't do this. So yeah, 140 max, it's not a good thing, Andrew.
All right. Any other questions, guys? We got
Good question.
Yeah, that's a good question. We have about 5 more minutes.
Yeah, I mean, there's a lot of information out there on air-to-water heat pumps. Obviously, there's lots of stuff in the magazine about it. There's lots of stuff on the YouTube channel. If you follow Leah and I on LinkedIn, we don't have the same LinkedIn, by the way, but if you reach out to Leah on LinkedIn, if you reach out to me on LinkedIn, I write articles weekly. I don't know why. I'm trying to get good for when Leah has them. But I've written a lot of articles at air-to-water, good, bad. I've shared pictures. There's lots you can read.
We got another one, Mike, actually. So we got one from Tyson. So would you still suggest a heat pump system in a place like Alberta, where electricity costs tend to be a lot higher than natural gas?
Yeah, Tyson, that's a great comment. So where I get myself in trouble is when speaking of LinkedIn, go on my LinkedIn and see my praise of Enbridge and Fortis, and then the heat pump people are like, Mike, what are you doing? And so my attitude is, again, going back to the people before profits. And this is where it goes with Tyson. If I come into you in Alberta, and to be clear, I have no idea what your electrical rates in Alberta are. But if I come into Alberta and say, hey, Tyson, you need to do a heat pump because I said so, or because some government policy said so, and at the end of the day, it ends up costing you more money, I am putting my agenda before you. And I have a problem with that. I believe that every solution should suit that person. The reality is there's other options. One of the things I'm going to look at, actually Leah and I are going to look at, is we're going to look at a gas absorption heat pump. So we're going to look at a commercial one. Good news, we're filming it. We're putting it on the YouTube channel, and we're looking at a residential one, because I'm of the opinion that if a gas absorption heat pump can do what Tyson needs in Alberta, it uses less gas. That's still good. If you look at the drawing I just had, Tyson, in your scenario, you could be doing what was in my drawing. You could have an air to water supplemented by gas, and it could be as simple as the air to water shuts off at a time of day where it doesn't make sense to use electricity. Or maybe you're using that thermal battery. Maybe you're using that thermal battery to charge it when it makes sense to be charging it. So I don't believe we can paint all of Canada with the same brush. Like, I know nothing about Alberta, and I think the policymakers maybe also know nothing about Alberta. I don't know. I'm just making small talk, but we need to engage with everybody. Leah and I shouldn't make all the decisions for everybody in Canada any more than a couple of policy people should. Leah thinks we should. She's got the laugh like, no, we should. So, in your scenario, Tyson, I'd have to know more to suggest a heat pump, but if you shoot me an email, I'd love to talk about it, learn more. I've got friends that live in Calgary. I think that's close to Alberta. Geography fail 101.
Awesome. Okay.
Hopefully that answered, Tyson. That was kind of a tirade on my end.
Any other questions?
Yeah, if there are any questions after this, you can certainly reach out to me. If you don't have my contact information, Leah 1000% has it. If
Yes.
you look me up on LinkedIn, as I say, I'm not a shy guy. I'm not afraid for people to challenge me on what I'm saying here. I've done this for 2 decades. I'm a firm believer that you continue learning, and I learn as much from doing these and talking to people or engaging through chat with people. And I definitely value everybody making the time to be here today. And hopefully you learn something new and neat.
Hopefully. All right. So we have a minute 30 left on my countdown. So does anybody else, stragglers, have any more questions? We'd love to answer some more.
Yeah, somebody throw out a question for Leah.
Yeah, please. I don't know what we're going to do to fill up that minute and a half.
Nobody wants to take that bite. I wish we could see, like, if there was dots if people were typing to see how many people are thinking of a question for Leah about hydronic heat pumps. She's pretty good, guys. She can probably answer it.
Oh, I was literally just thinking, don't ever expect me to answer any of these questions. I just edit his articles.
As you can tell, we have too much fun. You can't take life too seriously. working on mechanical systems is a challenge. We unintentionally do stupid things, and I'm one of those people that doesn't believe in stupid actions or stupid questions. I just believe in stupid answers, right? Like, don't be afraid to ask questions. I'm not afraid to ask questions. Don't be afraid to admit defeat, because honestly, it's not defeat. If Andrew makes a mistake and says, "Hey, Sarkis, help me," that's not defeat. That's help. I talk to Andrew and Sarkis all the time, seeking guidance on stuff, and I'm sure other people in the chat that haven't said hi. I'm sure I know quite a few of you. It's a challenging industry. We got to have fun, and we can't be afraid to make mistakes. The key is to learn from those mistakes.
For sure. All right, I think we can let them go. So, okay, so I'm gonna say we're gonna shut down this session. We got our speed meeting starting up shortly. I can tell you at 2:25. So we got 5 minutes until everyone can join in on that. Otherwise, we have our next session at 2:45. All right, thank you all, guys. Thanks, Mike.
Thanks, Leah. Thank you for coming, guys.